All right, so this is lesson 2.2, free body diagrams and net force. This is part one. So the learning target, I can analyze forces through the use of diagrams and mathematics. At the end of this lesson, you'll be able to define what a free body diagram is, equilibrium, and net force, and you'll also be able to draw free body diagrams to represent different types of motion. So what is a free body diagram, right? It's like, oh, well, it's a diagram. So clearly it must be some sort of drawing, which is exactly what it is. But it is a particular type of drawing. So it is a drawing of all the forces acting on an object. We are going to use arrows, right? So our arrows have the arrowhead, which indicates a direction, and the length of our vector indicates a magnitude. So simply put, it's a vector diagram. It has to be labeled correctly. So that's kind of where it goes from being simple to maybe just one step up. It has to be labeled correctly in order for you to get full credit. So how many types of motion are there in physics? Well, we've only ever talked about three. So the first one was an object at rest. And so an object at rest, if it's simply sitting on a surface, you're just going to have a force of gravity pulling down, which is what we denote as Fg. So it pulls us down, and that should be the same idea of what we've always been talking about with gravity when we talked about it in kinematics. We also have this force pointing up, right? And we label it Fn. Fn is known as the normal force, and we will talk more about it in lesson 2.4. Okay, so if you take a look at these two forces, right, we have the normal force, right, and the gravity force. So if you take a look here, the length of these vectors are identical, and they point in the opposite directions, okay? So with that being said, since they point in opposite directions and they are the same magnitude, if you were to add those quantities together, whatever numbers they would simply cancel out, okay? Because they have the same magnitude and they're pointing in the opposite direction. Okay, so that's a really big idea. Also, when we draw a free body diagram, you have to have this dot in the center. You don't get to put in the forces at any part of the squares. So that means like I can't put something over here and label it with forces. That's no good. Okay? You have to put that dot in the center of your object, right? That is like the center point, and your vector quantities, right? Your forces, they have to originate from that dot and move either up, down, maybe right or left, right? So the next type of motion we talked about were objects that traveled at a constant velocity. So we are going to have a normal force and we are also going to have a gravity force. However, this time we're going to have a force of friction, which we denote as FF, and a force applied, which we denote FA. Please be sure to include this arrow right here, showing that the object is in fact moving, because when we get to lesson 2.4, we will also see that you can have all four vectors, but a certain scenario happens and you might not be traveling at a constant velocity anymore. So make sure that you are putting that velocity arrow in. That is very important above it. So here, just like before, we know that the normal force and the force of gravity cancel out, right? If you take a look at the force of friction and the applied force, you also notice that they are in fact the same magnitude and they too are pointing in the opposite direction. So just like before when we canceled out the normal force and the gravity force, we can also do the same thing. We cancel out the force of friction and the applied force. And that's how we can justify it's moving at a constant velocity since all the forces cancel out. Okay? The final type of motion that we spoke about in our class in kinematics was an object that was accelerating. So here you do see something a little different. So let's take a look at our vertical forces, the normal force and the gravity force. Just like all the other types of situations, they're in fact the same magnitude and they're going in opposite directions, which means we can cancel those out. So we do not have any force in the vertical direction, but what's different is that the force of friction and the force applied are no longer the same length, right? As we can tell, the force applied is clearly a lot longer than the force of friction, indicating that I can't cancel these out because I'm still going to have a little bit more of the force applied left, okay? And later in this lesson, we're going to talk about what that leftover value means. So with that being said, if you remember from Newton's first law, Newton's laws lesson 2.1, we know that the acceleration has to follow the same direction of the force, right? So because we have a leftover force on the right side where the force applied is, our acceleration points in that direction. So here only the vertical forces can cancel out, but the horizontal ones can't because we'll be left over with some sort of value since they are not the same magnitude anymore.